Hey students, today is day 1 of section 5.5, exponential and logarithmic models. So now how do we try to fit these functions to actual real world data? And do the models we fit, are they perfect? Are they pretty good? Or are they terrible? And that's all kind of based on our R squared value. So remember, R squared is something you got to make sure is turned on your calculator. We'll show you how to do this in case you've forgotten or just never really learned it, I guess. Exponential models have this form right here. Y equals a times b to the x, and on our calculator, the regression is going to be exponential reg. Logarithmic models have these two forms. You got y equals a plus b times log x, or a plus b times ln x. And the form that our calculator has is the natural log regressions. So we're going to be looking for this ln, natural log regression, on our calculators. All right, so let's make sure that diagnostics turned on. So whichever model has the R squared close to 1, that's the best fitting model. Make sure diagnostics turned on. So if I go to my calculator here, second 0 is the catalog menu. Go all the way down to diagnostic on. You can hit the D button to get there faster. Diagnostic on, enter, enter, enter. Now we should see our R squared every time we do a regression. Okay, so let's jump right in. I wanted to try to find some kind of real world data that would work here. So we got a little bit of old data here on the moose population in Minnesota from the DNR. The moose population actually has rebounded a little bit, so this data makes it look bad for the moose in Minnesota, but current data is pretty good. Here's the data set we're going to be working with today for our first example. So we've got the year and the survey estimates from the DNR on how many moose were left in Minnesota. So first thing, maybe you kind of remember doing this from previous chapters. First thing we should really do is pick a year 0. We don't want to put in 2005, 2006 into our calculators. So let's take the year 2000 and make that our x equals 0. So sorry, my pen is kind of acting up today. So the year 2000 is going to be our x equals 0. So that means 2005 is going to be 5. 2006 is going to be 6. 2007 is going to be 7. Then we got 8, 9, 10, 11, 12, and 13. So we want to put that into our calculator. Let's do that right now. All right, let me pull up the calculator. So stat, enter on edit. We're going to type that data into our list 1 and our list 2. So 5, 6, 7, 8, 9, 10, 11, 12, 13. All right. And then we want to put the moose population into list 2. All right. I'm going to pause it here while I type all this in so you don't have to watch me do it. All right. So we got the data in. So we want to find what model is best. And let's just look at the two new models. So hit the stat button, go to calc. We could check linear models. We could check quadratic models. We could check power models. But let's just stick with the two that we have just been talking about looking at in this section. So first one is the exponential regression right there. Enter. List 1, list 2, enter, enter, enter. No frequency list. We're not going to store it. Just going to go to calculate. All right, so the r squared, I'm just going to take a picture of this. The r squared for our exponential model is 0.805. 0.805. Okay, so then let's see what the logarithmic model says. So stat, calc, and then you might, if you look for logarithmic, you might end up at logistic, which is something different, which we'll talk about in 5.6. Remember, we're looking for the natural log, ln reg. That's our logarithmic model. So ln reg, natural log regression, and we get an r squared of 0.76018, blah, blah, blah. So if my only two choices were between these two, I would have to go with the exponential model because this one has the r squared closest to +1. Okay, so this model is better than this model. All right, so we would say y equals 1858, let's just round to a whole number here, times 0.882 to the x. I rounded to 3 decimal places. Maybe could have gone to a 4th decimal place, but let's see how that works out. So if that's the model we're going to use, let's take a look at it with our scatter plot and our graph, and then let's see if we can answer this question. When will the moose population drop below 500? Okay. So back to the calculator. Y equals, let's clear out this old stuff. Okay, 18588, all right. 18588, and then 882. Oh, I'm in Y2. Oh well, that'll work fine. To the x power. All right, so I'm going to turn my scatter plot on, and let's just see. Let's do hit the graph, and I'll just hit a zoom 9, and we kind of see how well that curve is kind of fitting the data. It doesn't look super great to me. I think maybe something a little bit more curved this way. Maybe a quadratic would have been better. But we were just comparing these two different models, exponential and logarithmic. But I didn't answer the question. The question says, when is it going to dip below, when would we expect the moose population to dip below 500? Okay, well, a couple different ways I could solve that. I could go to my table, and I could look for where y2 is less than 500. And you can see right around here, year 30, year 29. Or I could go back to my y equals and I could put 500 in, and we could see where they intersect. Zoom out a little bit. And for y min, I'm just going to put 0. All right, so we see the moose population going under 500 where they intersect here. Second trace, intersect, enter, enter, enter. 28.795, so almost 29 years. Is when the moose population goes below 500 based on an exponential model. Okay. All right, let's try another example. Life expectancy in the United States. I found this table. It's the life expectancy based on the decade you're born in. So where 1900 is our x equals 0. Sorry, my pen is acting crazy here. But so when we have a 1 here, that means if you were born in the 1910s. When we have a 2 here, that means if you were born in the 1920s. So we got the 30s, the 40s, the 50s, the 60s, the 70s, the 80s, the 90s. And then 10 would be if you were born in the 2000s and 2010s. Okay. And this would be the 2020s. So not too many people born in the 2020s. We just hit 2020. So let's check out how well a log regression fits this data. Okay. So we got to kind of clear everything we just did. I'm just going to start by clearing my y equals. Okay, stat, enter, and I'm going to change out this data. I'm going to clear out this old data. All right, I'm going to pause it here so you don't have to watch me enter in all the data. Okay, I got my data in. Let's see what the natural log model for this is. So stat, over to calc, ln reg, list 1, list 2, enter, enter, enter. Pretty good r squared this time for our natural log model. Y equals a plus b times ln of x. Our a is, let's call it 42.5. Our b, let's call it 13.9. So 42.5 plus 13.9 natural log ln of x. Okay. And let's hit graph and then zoom 9. And we can see how this log model is fitting that data. Looks pretty good. All right. So I'm just going to take a quick picture of that and bring it back over to where the notes were. Okay. So the question then would be, let's suppose, oops. Here's the question. What would we expect the life expectancy to be of somebody born in the year the decade 2100s? Okay. So remember, if 1900 was x equals 0, the 0 decade, and if x equals 10 was the 2000 decade, then 2100 is going to be the x equals 20 decade. The 20th decade after the year 2000, after the year 1900. So we just need to go to x equals 20 on our calculator table. So second table, I'm already kind of there. Here we are, x equals 20. Or we could plug it into our equation, but probably just easier to use the calculator. All right. So at x equals 20, we've got a y. So our function when x is 20, we have 84.14. So we have a life expectancy of 84.14 years. All right, let's have you try the next problem on your own. What is the best model for this data, and what will the value of y be when x equals 10? So this is just some made up generic data. Now you have 5 different types of models you can test: linear, quadratic, exponential, power, and logarithmic. All right, go. See if you can figure out what the best model is and what will the value of y be when x equals 10. Okay, the best r squared I got was with an exponential regression. And when I plug 10 in for x in that equation, I get a value of 284.8. Hopefully you got the same. All right, today's homework will be on quizzes. Hope everybody's doing well. Give me an email if you have questions. Bye.